Okay, Zoe, can you hear me? And
Yeah.
screen shared? All right, so we are live on YouTube. Okay, so today we're going to do a recitation which is focused on sets and proofs involving sets. To start, there's some announcement. We're currently grading homework 2. Quiz number 1 scores are out. So you have, according to the class syllabus, you have 1 week to request regrading after receiving your grade on Gradescope. Most importantly, quiz number 2 is next week. It's next Tuesday, September 29. Please mark your calendar. It's the same as quiz number 1, where it starts at 7:30, close at 4. It's going to be on proofs, which is actually chapter 2 of the textbook. And right now, of course, we're covering sets, which is chapter 3, but the exam is going to be on chapter 2. Okay. The only difference compared to the previous quiz is that we have extended the grace period. So in the past, you have 15 minutes and, we extended to half hour. So after you have spent the entire 60 minutes solving quiz number 2, you should dedicate the remaining 30 minutes for your submission purpose only. Do not try to use that time for solving the quiz, because you do need to reserve time for submission. So we will not, accept any excuse other than what we call medical emergency for quiz 2 makeup. And a fair warning that historically quiz number 2 on proofs is the hardest among all quiz. So you should prepare accordingly. Of course, there is already a practice quiz, number 2, that is available over Canvas. So you should try to solve it on your own to see where might be some of those holes in your current knowledge, and then come to office hours and use Piazza to ask a lot of questions. Another place where you can get material is go to read the Canvas under how to get help, and how to prepare for quizzes. One other good place to get a lot of practice problem is, in fact, your own textbook. So if you go to the textbook at the end of each chapter, there's a bunch of questions. Some of those show up in your actual homework, but some of those problems is in blue, and then they have corresponding solution provided at the end of the textbook. So this is also a very good place to get more practice problems done to get ready for quiz number 2. So what is on quiz number 2? Typical proof techniques, things like proof by contradiction, proof by induction, proof by contrapositive statement, proof by cases, and so on. So, and also, of course, a lot of those proofs, you are going to see basic algebra that's going to show up. For example, integer divisions, a mod operation, taking remainder, whether an integer is divisible by 4, divisible by 5, divisible by 9, and so on. So, so fair warning, spend enough time prepare for quiz number 2 because it's not easy. Homework number 3 is also out. It is due on Friday, October 9. So typically homework on average is due every 2 weeks. We made it to due 3 weeks so that you actually have more time to prepare for the quiz. So the homework 3 is not due in the same week of the quiz, okay? But you should still start sooner with your homework. Do not wait until the due date to try to solve homework problems. All right, any questions before I move on to practice problem today?
There are a few questions in the chat just regarding proofs in general about seeing a lot of examples of like sketches of proofs and not full proofs.
Right. So in the recitation, because we're constrained by time, so we go through a lot of proof sketches, and a lot of those problems actually in the next slides we have, especially for the lecture problems, we actually have the detailed proof written down. So if you are preparing for the exam, you should go over also the slides from the lectures as well, because a lot of those problems we have typed in details, but we have not typed in detailed proof for every single question we are going to go through. But if you have questions, please come to TA office hours and we can go over detailed proof step by step. Unfortunately, we didn't write detailed proof for every single problem because we're constrained by time during the actual recitation. But if you have questions, please post it over Piazza or come to office hour.
All right, and then Ashton, go ahead with your question.
Yeah, so I'm just wondering, what is quiz 2 all the chapters covering? Are we, I guess, like what lectures is quiz 2 covering?
I'm going to make a typical announcement, but if you go back to Canvas under modules, that if you go over all the modules that is surrounding the proofs, for every single lecture, there is a specific section there that says, read chapter 2.1, 2.2, and so on and so forth. You take a union of those, that is what you need to read. But I can make a specific announcement later on today. But
Okay.
It's already available when you're preparing or watching the lecture that is associated with the proofs. For each of those lecture on Canvas under modules, is already specified what chapters you need to read anyway. But I will collect that and make announcement.
Okay, thank you.
Yeah, but to be clear, for your actual exam, you do need to write detailed proof, right? To say, okay, if something is 2 times p plus n, so you have to say by the closure property of integer integer close under addition, p plus q is an integer, therefore, this is an integer. So you need to actually spell out all this. There's actually plenty of examples of detailed proof from the lecture slides. So you should go over that to see how a detailed proof is written. The textbook also contains detailed proof for all the examples in there. Okay. All right. Okay, so a quick review, right? Symbols for set definitions. This is for chapter 3, which is going to show up for quiz number 3. But from chapter 3 onwards, you're going to see proof show up multiple times. And all the proofs I'm going to go through today are proofs regarding sets and so on. Okay, so just a quick review of sets definitions and what's a property. So if I have the notation A is a subset of B, right? So you have this notation here. This means for all element in A, it's also in B, okay? And the next one is A is a proper subset of B. What does that mean is, number one, it's A is a subset of B, but there exists an element in B that is not in A. So one way to think about this is that if A is a proper subset of B, there's some element in B that is not in A. So in other words, that B is strictly larger than A in terms of number of elements. And of course, the last one is when 2 sets are equal. The property you're going to use quite a bit in proofs of set equivalence is to prove 2 sets are equal, you need to prove A is a subset of B and B is a subset of A. When both conditions are satisfied, the 2 sets are equal. And another way to think about this property is for all element in A, if and only if is in B. So other way is for all element in A is in B, and for all element in B, it's also in A, okay? So this is just a quick review of some of those set definitions, and this is already described in the lecture slides and lecture videos associated with this week. The next one, of course, common symbols is empty set, which is a set that has no element. And then there is the last one, which is a universal set, or sometimes called universe. Is a set containing all possible elements in the context of the problem itself, okay? And in the context of the problem, every set is a subset of this universal set, okay? So if you think about the Venn diagram, the universal set is usually visualized by this square where every set inside is part of this universal set. So this is how typically you imagine what a universal set is. And the important part for a universal set is thinking about A's complement. For example, what is A's complement is everything in the universal set that is not in A, okay? So sometimes, depending on the textbook, depends on notation, sometimes people also using A of C as a notation for complement. But it would be clear in the definition of the problem to tell you this means complement. Okay, so proofs. So this is actually a proof not necessarily related to sets, but since our exam is coming up soon, so we're going to do a quick example by proof by contradiction. So you have actually 1 minute to think about how to prove this by contradiction. The proof is really 2 lines actually. So I'll start a timer. Okay, so this is the opportunity for you to go over how do you want to prove by contradiction. Okay, and usually when you prove by contradiction is you assume that there exists a counterexample, and that counterexample leads to a contradiction, which means the counterexample doesn't exist, which means the original statement is true. Okay, do I have a volunteer? You can type or you can unmute yourself. You can raise your hand. It's how would you prove it?
First, assume the contradiction that there are 2 integers that satisfy that.
Okay, so you say assume counterexample exists. So that is there exist x and y, which are integers, such that 24x plus 12y is equal to 1. Okay, all right, so that is assuming counterexample exists. What's the next step?
Factor a 2 out of the left side, so you get 2 times 12x plus 6y is equal to 1. Then by closure, you can turn the 12x plus 6y into a single integer, so you get an even number is equal to 1.
Yep, and that's a contradiction. Great. Okay, so if I write out what you just said in detail, I'm factoring out 2 from the left-hand side. Okay, and then say by closure property of integer under addition, maybe I'll use a variable, let k is equal to 12 times x plus 6 times y. Since x and y are both integer, k is in the integer. Okay, since x and y integer, k is integer. So we have 1 is equal to 2 times k. Okay, and then by definition of even number, 1 is even. Okay, because 1 is 2 times some integer. And this is a contradiction because 1 is odd. Okay, so that means the counterexample does not exist, and that means the original statement is true. Okay, so the important part of this proof is really, as what you said, the factorization of 2, and then eventually it leads to the contradiction that 1 is an odd number by derivation, but we know that 1 is, by derivation, it says 1 is an even number, but that's contradict the fact that 1 is an odd number. So that's a contradiction, okay? And then of course, in the actual exam, you want to say this is a contradiction because 1 is odd. Therefore, counterexample does not exist. Does not exist. And the original statement is true. Proposition is true. That's the end of the proof. So also you can say, instead of saying the original proposition is true, you can say where there are, you can just repeat it to say, therefore there are no two integers x and y such that 24x plus 12y is equal to 1. Okay. All right. If there's no question, I'm moving on to next one. Again, this one is more about proofs, less so about sets. I promise we'll move into some proofs about sets, but we're going to do a few examples that is relevant for quiz 2. Okay, so you might have seen this already. This is a quick review because this is a slightly tricky question. But since you might have seen this already, I'm going to give you 1 minute to actually think about what are the approaches you might take when you see a problem like this. And this is a typical proof by induction where the proposition involve manipulation using some basic algebra. For example, in this particular case, we provided a hint of how to expand x minus 1 to the power of fifths. And because we provided this, it sort of give you a hint, at least part of your proof might use this formula. Okay, so of course, whenever you do induction proof, think about the 4 steps. What is my problem statement? What is my induction? What is my base case? What is my induction hypothesis? And what is my induction step? Okay. So it's important to be able to solve this one. Do I have a volunteer to tell me both what is a problem statement and what is a base case? Well, this is going to be a typical question. Yeah, go ahead.
You have a volunteer.
Sorry, go ahead, Matthew.
The problem statement is just that for each integer n greater than 1, 5 is divisible by n to the 5th minus n.
Mm-hmm.
Yeah.
Okay, I'm going to write it in a way that this is correct, but I'm also going to write it in a way which is equivalently to say, instead of say 5 divides n fifths n to the power of 5th minus n. Remember, when you divide something, there's an equivalent way of saying it is to say that n to the power of 5 minus n is equal to 5 times q for some integer q, right? So this is sort of equivalent way of making the problem statement. And in this case, you are going to use this property anyway, so you can actually put it at the part of the problem statement. But what you said is also correct. So this is just alternatively, you can say this. Okay. All right. What is a base case?
We use n equals 1 and plug it in.
Right. So what is base case is to say, show, let me call this P of n to be this entire statement. Okay. So I want to show this statement or proposition P of n is true for n equal to 1. Okay. So now we want to validate. So we want to show, essentially, we want to show 5 divides 1 to the power of 5 minus 1. Okay. So 1 to the power of 5th minus 1 is equal to 0. And that's equal to 5 times 0. So that is essentially proved, right? If you want to write it out, 0 is an integer. So 0 is 5 times some integer, therefore 0 is divisible by 5. So this proposition is true for n is equal to 1. All right, anyone tell me what is the hypothesis?
All right, in the chat, assume P of n is true.
P of n is true for n, right? Which is true. Just assume P of n is true. That means I'm going to spell it out. 5 divides n to the power of 5 minus n, which is equivalently, say n to the power of 5 minus n is equal to 5 times q for some q in z. Okay, so great. What is the induction step? What do we want to show? Anyone?
In the chat, proof for n plus 1.
Yes. So to prove n plus 1 is true, it means we want to say 5 divides n plus 1 to the power of fifths minus n plus 1. Okay? So this is really now, this is, once you set up those 4 steps, now we are going to potentially use the hint, which is looking at this formula, of course. So what are these formulas try to tell me? For induction hypothesis step, I have the formula n to the power of fifths minus n. And here I have n plus 1 to the fifth minus n plus 1, okay? So somehow I should be able to use this formula. But here is a little issue, actually. So these 2 steps is perfectly fine. But because you are using from Pn to Pn plus 1, what you might end up using is the different hint, which is going to be the hint of x plus 1 to the power of 5 is equal to x to the power of 5 plus 5x4 plus 10x3 plus 10x2 plus 5x plus 1. I think this is the right formula when it's doing x plus 1 to the power of fifths, okay? So because then you can expand n plus 1 to the power of fifths minus n plus 1 into this formula and then using induction hypothesis, okay? But equivalently, to make our life slightly easier, like I said, assuming Pn is true, proof Pn plus 1 is true, you will still be able to do it. It's just most likely you'll end up using this formula instead, which is also coming from binomial theorem. But instead, this is V1, V2. You can, again, induction hypothesis is to assume P of n minus 1 is true, which means n minus 1 to the power of fifths minus n minus 1 is equal to 5q. And then induction step, you want to show P of n is true. Okay? I'm only doing this because I want to use the original provided hint, but you can also use the new hint I provided there to also solve it. Okay? So let's see if I have space. Yes. Well, let me just do it here. Actually, I could add a slide. Yes. So let me add a slide. I will rearrange it later. Okay, so the last step, induction step, let's again using the things where we assume P of so this is continue. We assume P of n minus 1 is true. That is n minus 1 to the power of fifths minus n minus 1 is equal to 5q. For some q integer, this is induction hypothesis. And induction step, we want to show P of n is true. That is 5 divides n to the power fifths minus n. Okay, so now this is the important part. Using induction hypothesis, we have n minus 1 to the power fifths minus n minus 1 is equal to 5q. What you have is you just use the hint. Using the hint, you expanded n minus 1 to the power fifths. So on the left-hand side, you get n to the power fifths minus 5n4 plus 10a3 minus 10a squared plus 5n minus 1. Okay, and then minus n minus 1 is equal to 5q. And from here on, remember my goal is to arrive at n to the power fifths minus n. All you need is some rearrangement. So rearrange. I only care about what I highlighted in yellow. Oh, here. So what I have is n to the power 5 minus n, right? I just take 2 terms on the left-hand side, and I move all the terms to the right. Of course, there's also additionally minus 1 and minus 1 cancel out. So the right-hand side I have is 5q plus 5n4 minus 10n3 plus 10n squared minus 5n, right? This is just rearranging the equality from left to right. And then now the next one is factoring of 5, okay? If you take 5 out, you get and then by the closure property, everything in the parentheses is integer by closure property, okay? So therefore you have proof that n to the power fifths minus n is 5 times some integer, where let k equal to this, okay? So that's really is a proof sketch. And if you go back, we actually have, for this example, we have it spelled out of the detailed proof, okay? So the most important part of this induction proof is to use essentially this formula when you are trying to adapt to the induction hypothesis, and then you are going to do some rearrangement and recombination. Okay, I think somebody's raised hand. Go ahead.
So I have a question about the last step, the induction step, because for me, I thought that we were trying to rearrange our what we're assuming, or not what we're assuming, but so we're going from p of n minus 1, which we assume is true, and trying to prove p of n, right?
There's
and
2
so
ways. You can
yes,
prove,
well, in this case, in this specific case, it doesn't matter the case, because I run into this problem myself often.
Okay.
Where I just get stuck somewhere in there trying to do this substitution.
Yeah.
How come you could go to the assumption that we made and make use the hint in the assumption that we already know is true when we didn't? I don't see how we connected the assumption to the next step.
Yeah. So this is really at the center of an induction step. Okay.
Yeah.
So at the center of induction step is to say the following. First of all, let's have a problem statement. And this problem statement in this particular example, we want it to be true for or integer bigger or equal to 1. Okay. So I'm just going to explain to you in a different color the philosophy behind induction proof. And I'm going to use this problem as an example. I want to prove my statement is true for a bunch of integers. I want to prove it's true for integer 1, integer 2, integer 3, integer 4, and this goes to infinity, okay? So, of course, the naive way to prove it is to prove that my statement is true for every single integer independently, right? So I can say, okay, is this statement true for 1? So let's say is 5 divisible by 1 to the power fifths minus 1, which is 0. Is 5, can 5 divide 0? Okay, it's good. Now, the moment I move on to the next one is 2 to the power fifths minus 1. to the power of fifths is equal to 30, minus 2, which is 32 minus 2, right? So that is 30. So, okay, this statement is true for that. And then, of course, now the problem immediately become complicated when you move on to 3, okay? So, of course, if my set I want to prove is finite, I can do this naively. And if my set is infinite, I can't do that directly. So instead, I want to rely on the following. First of all, I want to show a base case is true. So when I say a base case is true, that means I want to show the first number in the sequence I want to prove is true. That's why we say the base case is true when n is equal to 1, okay? And we showed that it's true because n 1 to the power fifth minus 1 to 0, then that is divisible by 5. So 5 divides 0. So this is true for the first case, okay? Now, induction is the following, is assuming this is true for a number that is n minus 1, I want to prove it's true for the next immediate number, which is n, okay? And assuming I have successfully proved the inductions in the induction step, which means whenever the statement is true for n minus 1, it's true for n. How can I go back to my original statement? Because I have proved, starting from n equal to 1, because my statement is true for n equal to 1, okay? And I proved whenever n minus 1 is true, n is true, then I put n to be equal to 2, which means whenever the first so when n is equal to 2, what is n minus 1? It's 1. So it says whenever it's true for 1, it's true for 2, which is the next number. Okay, so that is the induction step. So whenever I first prove the base case to say it's true for n is equal to 1. And now I always say somewhere in here, whenever it's true for n minus 1, it's true for n. So my induction hypothesis is assuming it's true for n minus 1, and we prove it's always true for the next immediate one. How can we use this? Going back, because I proved whenever a number is true for a number, it's true for the next number. So now I go from the beginning. Since I already proved the base case is true, meaning that this statement is true for 1, it has to be true for the next, what's the next number adjacent to 1? Which is 2. So 2 is true. But whenever 2 is true, based on my induction hypothesis and the induction proof, the next one is true. So now I can sort of propagate the true statement going from 1 to 2 and going from 2 to 3 and so on and so forth. So that is really at the root of induction proof. Is you start with a base case, you show the base case is true. And then in the induction hypothesis, you assume this statement is true for any number that is n minus 1, where n is a variable.
When you're done with class, can you clean the kitchen? I'm unmuted right now. Yes, continue. Sorry.
Okay, so then you move on from n minus 1 to n, which means the next immediate one adjacent to the current one is true, if the current one is true. So if the statement is true for 1, then it's true for the next one, which is 2. Whenever it's true for 2, it's true for the next one, which is 3. Okay, so that is the philosophy.
And then there is a question in the chat. Can we assume that Pn minus 2 is true and then prove for Pn minus 1?
Yes, but you have to be very careful. Remember, my sequence starts in this case from 1. Okay, so if you want to say assume, this is not typical, but it may happen. If you want to induction hypothesis to say assume Pn minus 2 is true, you want to show Pn minus 1 is true, then you better make sure that this n minus 2 reach my base case. Okay, because when n minus, so what is n minus 2? So n minus 2 has to be bigger or equal to, say, 1, right? That's number one. So n is bigger or equal to 3. So if you want to do that, then you want to have to at least show P1 is true. Okay, and yes, so you have to say, assuming Pn minus 2 is true, and you need to specify where does n start. In this case, it's for n bigger or equal to 3. Okay, so you can always do that, but I would say that you need to be very careful about whenever you want to like go backwards a few more steps, you want to make sure your variable goes in is still valid. Okay, so you want to say assume Pn minus 2 is true for n bigger or equal to 3. So you make sure you cover your base case. But also typically, it will not make your problem easier because, for example, if in this problem you want to assume n minus 2 is true, then you get something like n minus 2 to the power 5 minus n minus 2. Now you need to expand n minus 2 to the power 5. All right. It's still doable, but algebraically slightly more complicated.
And just before we move on, because the part I was struggling with, maybe this was just me, but it was the connecting what our assumption was to the thing that we were proving in the induction step.
Oh, yes.
So,
okay.
So like what you have your induction hypothesis that you plug in here, and then you solve it to make it part of it equal to the next thing. Is that typical for induction?
Yep.
Things where typical. Okay, so you usually use, because I mean the way I was doing it, I think, and this was wrong, is I would manipulate, for example, I would try manipulating the n to the 5th minus n to try to create an n minus 1 to the 5th minus n minus 1 and do substitution there for 5q. I just like,
it's pretty hard for if you just do it directly, but here's the beauty of induction proof. Somewhere in your inductions, in your 4th step is an induction statement, right? You need to use induction hypothesis somewhere. That is something you really need to keep in mind. Like if you get stuck, you want to go back is to say, does my current proof include using the induction hypothesis? Okay. For example, if you go ahead and start playing with n to the power 5th minus n through some algebraic manipulation, most likely you'll get stuck. Now the question is, can I go back to something I already assume is true? Have I used that already? Have I used my induction hypothesis already? The answer is no. Then you go back to the induction hypothesis to say, what kind of hint does it offer me? Induction hypothesis, in this case, contains the term n minus 1 over 5th, and we actually give you a hint to say n minus 1 to the power of 5th can be expanded to contain a term that is n to the power of 5th. So this is where the connection is between induction hypothesis and induction step, because you are connecting n minus 1 to the power of 5th to n to the power of 5th. So that is really, I mean, to be fair, that is the tricky part of this problem, is to make sure you understand the connection between these two terms. And then the rest is algebraic manipulation. So the goal is you want to be able to arrive at this n to the power of 5th minus n from induction hypothesis. So really the key is understand the relation between these two expressions. Okay. All right. If you have additional questions,
thank you.
Yeah, go ahead.
Just one more in the chat. So by rearranging, we build P of n from P of n minus 1.
Exactly. That is really the key idea. Okay. Now, one more proof, pigeonhole principle. You also see this, right? And also this is a problem we have seen before. So I'm going to just at least, let you think about it for, again, a minute and to see how you solve it. Since this is, again, a problem you might have seen before, we're just going to talk about sketch. Okay, and then we can finally move on to a few examples for proofs involving sets. Okay, so here, giving any 7 integer, there will be 4 for which the sum of the square of those integer is divisible by 4. So as I mentioned before, when you use pigeonhole principle, there's a few things to keep in mind. Number 1 is how many objects. Number 2 is how many container or buckets. Number 3 is how many item per bucket. I'm using the word bucket and container interchangeably, okay? Can someone tell me how many objects are there?
7.
Great. How many buckets?
4.
Yep. Well, not really. So remember, there will be 4 of which the sum of square. So 4 means how many item per bucket. So actually what this problem first tells you is it tells you m plus 1 is equal to 4. So m plus 1 equal to 4, meaning that there's 4 items in one of those buckets. How many items? Let me to be more accurate. How many items in at least one bucket? Okay. So in this case, it said there will be 4 in one of those buckets. So m plus 1 equal to 4. Now you need to solve for n. Okay. Now you solve for n, 1 and 2. You solve for n. N is actually equal to 2. So you have 7 integers you put into 2 containers such that each container contains, at least one container contains 4 numbers. Okay. So now I have used pigeonhole principle. The key idea behind this problem is to how to design the buckets. I know that I need to have 2 buckets. Now I need to design the buckets so that it satisfies the problem statement. There's one property in the problem statement that we have not used. That is the sum of the square of those 4 integers is divisible by 4. So somehow, yeah, go ahead.
Just in the chat, someone suggested even and odd for the buckets.
So this is really maybe I will consider a trap of this problem. If you try to do even and odd, it's not easy and you might get stuck somewhere. I will ask you to try even and odd buckets. Okay, I would ask you to try it and to see if that's doable. Actually, in this case, perhaps both of them are doable. Okay, so let's say if you try even buckets and odd buckets. So what is even and odd? That means if I mod 2, it either has a remainder of 0 or a remainder of 1. Okay, so actually in this particular example, even and odd buckets will also work, I think. Okay, so what is my proof? Does someone want to volunteer? What is a high level? Of course, everything I wrote down here is a sketch. Do we have? Go ahead, Jackson.
Remainder 0 and 2 and remainder 1 and 3.
Yes, that's a different version. Yeah. So I must say both of those buckets in this case will likely work. So for example, if I use what Jackson just said, remainder of 0, 2, 1, and 3, you are going to say what are the integers that falls into each of those buckets, what are the remainder looks like, and you look at the combination. But the version number 1, even and odd buckets will also work in a sense. For example, assuming if I'm going back to even and odd, I can say, okay, if they're or, so there's case number 1 and case number 2, right? So if they're or even, then let's say I have A is equal to 2 times M, B is equal to 2 times N, C is 2 times K, and D is 2 times P. okay? Now, if you take the sum of those square, you basically get sort of 4m squared plus 4n squared from 4k squared and so on and so forth. So you can factor out a 4. And so on, and you can say this is divisible by 4. For the second case, if they are all odd, you can do a is equal to 2m plus 1, b is equal to 2n plus 1, c equal to 2k plus 1, and d is equal to p plus 1. Again, you can take the square, and in this case, the square of 2m plus 1 is 4m squared plus 4m plus 1, right? Same thing with square of 2n plus 1, which is 4n squared plus 4n plus 1. So each one of those items has an extra 1, but there's 4 of them, so the sum has, you can factor out of 4. So that is also divisible by 4. So you can actually prove using even and odd buckets. You can equivalent prove by using the bucket by remainder by 4, which is remainder of 0, 2, or remainder of 1, 3. It just your number of cases grow, right? Because if I have 4 integers falls into the first bucket, then it can be 2m or 2m plus 2. Oh, sorry, 4m or 4m plus 2. If it falls onto the second bucket, it's going to be 4m plus 1, or it can be 4m plus 3. And there's 4 of them, so you have multiple combinations. So there's the number of cases grow much larger for the second version, but you can still go through with a proof. Okay. So finally, I would like to go over at least one problem surrounding set membership. Okay. I want you to prove that the set, let's call the set A, which is 4m m integer, and the set B is 2n n integer. I want you to prove that the first, so I want to show set A is a subset of set B. And the proof of this is really one line. Okay, can anyone volunteer how you would solve this? I can give you a hint. It's just one factorization.
Go ahead, Nathan.
So wouldn't you just want to factor a 2 out of the 4m right there and have 2 to the 2m? Then you would say that 2 to the 2m could just go to any integer. And so you'd have 2 of any integer is equal to 2n inside of the n.
Yep, exactly. That is the proof. So this is my sketch. Net x to be in A in this set. So by definition, because it's part of this set, it can be, this should be short lowercase, it can be 4 times m, and you factor out a 2, right? And then you can say 2 of n. Of course, here is by closure property, right, of integer under multiplication. So you can express any element in A as 2 times n for some integer n. That means this fits in the definition of the second set. You're done. So you want to say A, in order to show A is a subset of B, that means for all x in A, you want to show it's also in B. That's it. So for any element from the first set, you can express as element from the second set. This is the end of the proof. Okay.
All right, and then there's a question in the chat. Is it okay to use the same variable because we used n twice here?
It's fine because this is just a variable to say that this is expressed. It's n is a variable used in the definition of B. You can also use it here. But if you want to be careful, I mean, sometimes you do want to be careful. You can use any other variable, say P, and it's still okay because if x is 2 times P is an integer. It does imply x is part of, oh sorry, that x is part of the set B. Because any element in B can be expressed as 2 times some integer. X can just be expressed as 2 times some integer, so it's part of B. So in this particular problem, you can use n again, but if you are careful and not using n, you are using variable P, for example, it's still okay. because it has the same form, right? And it's just a variable in this term. In other words, the set is equal to the set. This two set is equal. Okay. All right. Let's do one more, and then that will be the end of the lecture. And again, this is a proof which is only 2 lines. Okay. I have 2 sets. If B has no element, we want to prove B is a subset of A. Okay. Can someone tell me what is a contrapositive statement? Do I have a volunteer? This is statement P. This is statement Q. Remember, I say P implies Q is equal to not Q implies not P. Okay, anyone?
In the chat, there is, if B is not a subset of A, then B has at least one element.
Okay, that's true. That is a contrapositive statement. And if I prove contrapositive statement, then I prove the original statement. Okay, so now suppose, right, because that's a part of a hypothesis, B is not A. Then by definition of not a subset, there exists some element X such that X is in B and X is not in A. This is just a definition of B being not a subset of A. That means there's some element in B that is not in A. Otherwise, B is a subset of A. Okay, so this is just using the definition of subsets. So if you have this, what's the next step? I'm like 1 line away from my proof.
B is an empty because it has X.
Exactly. Since X is in B, then B is not empty. That's it. That's the end of proof. Okay. All right. I'm not going to go into a proof, but let me make a quick overview. This is really the last question of today's recitation. This is also a very simple proof, but I want you to prove by two ways. I want you to be able to prove it by contrapositive statement, or you can prove it by contradiction. And I want you to challenge yourself to try to solve this problem by writing 2 types of proofs.
Real quick, there are a couple questions about
Yes.
the last proof,
Yeah.
about using the definition of an empty set since each set contains the empty set.
If B has if B has no element, then oh, I see. Okay. Good question. Yeah, so this is tricky because if you just say any set contains empty set as a subset, you effectively have not proved it, right? Because what it's asking you to prove is any empty set is a subset of another set. So you just pretty much restated the proposition. You have not proved it. So really this proof is asking you to prove that property. So you can't use that property directly. Okay, any other questions? Oh, any other questions? Okay, so as what I was saying before, I want you to prove this problem by 2 ways. Try to prove by contrapositive statement and try to prove by contradiction. It will help you kind of get used to both of those proof techniques. Okay, so yeah, feel free to use Piazza as well as office hours to try to get ready for quiz number 2, which is next Tuesday. Okay, all right, good luck.